Hello everybody, in this video we're going to cover section 3.4 in our text. We're going to learn how to define the concentration units of mass percentage, volume percentage, mass volume percentage, parts per million, and parts per billion. And we're going to learn how to perform some computations relating to these solution concentrations. So we're going to start off with the most common type of percentage that we see, which is the mass percentage. And we're going to see that really when we talk about percentage, even though we see it a lot on our consumer products and stuff, often we're not as clear as we need to be. And I want to kind of show you how that plays out here. So the mass percentage of a solution component is defined as the ratio of a component's mass to the solution's mass, expressed as a percentage. So I'm going to take the mass of the solute, the stuff I have in my solution, I'm going to divide that by the mass of the solution. I'm going to keep these units the same so that they cancel, and I get a unitless quantity here. And then I'm going to multiply that by 100%. So it's going to pick up the unit of percentage. Mass percentage is also often called percent mass, percent weight, weight percent, and other variations on this theme, which also just helps to add to the ambiguity. Okay, you may see all of these different terms used, but they always mean this exact same thing here, the percent mass. And the most common symbol for the mass percentage is simply just the percent sign. So when you see a percent sign, it's this much percent, that they're talking about a mass percent when they do that. But whenever we're doing this, we should be specific to which percentage we're talking about. We should write something like percent mass, percent weight. Weight percent is another thing you're going to see, or weight over weight percent. So mass over mass is what this little symbol here means. So anytime you see these, they're just trying to be more clear about which kind of percentage they're talking about. And just to give you an example, for instance, if you look on bleach is a solution of sodium hypochlorite and water, and it's going to have a percentage on there. Different kinds of bleach are going to have different kind of percentages. For instance, like those stuff that's specifically the germicidal disinfecting kind is going to have a higher percentage of sodium chloride on there, and that's a mass percent. That's what they're talking about. So now we have volume percent. So sometimes it's convenient for us to, instead of measuring the mass, because that's what I'm going to have to do to come up with this percent mass, right? I'm going to need to measure the mass of my solute, measure the mass of the solution, to instead, if I'm working with liquids in particular, to just measure their volumes. And then I can have a volume percent, right, where I have the volume of the solute over the volume of the solution. Now, this is a more problematic type of percentage and value than the mass percent, because while mass is completely conserved, volume isn't, okay? Actually, when you make a solution, the volume of that solution may change because the density has changed. It's also, the density is going to be dependent on the temperature. So the volume percentage that you're going to get at one temperature is not going to be the same as the volume percentage at another temperature. But for a lot of work, it's good enough to do this, and sometimes it's convenient. So you'll see people do this. And whenever you do that, you should definitely be making sure that you label that either percent volume or volume over volume percent to make it clear that it's different than the mass percent, because when you have solutions and stuff where their density varies a lot from one, you could get a very different value for your volume percent than your mass percent, and it could mean a very different thing. Again, whenever you're doing this, you need to make sure that the volume of the solute and the volume of the solution have the same units so that they cancel out. It doesn't necessarily matter what those units are. They could be milliliters and milliliters or liters and liters, but they need to be the same in order for this calculation to work out. And then the final one is going to be our mass volume percent. This is going to be a ratio of a solute's mass to the solution's volume expressed as a percentage. And this is just really a bad unit, and I don't use it. And the reason for that is if you have mass divided by volume, you're not going to have cancellation of the units. So it's not going to be independent of what unit you're using. All right. and it's going to be very, very ambiguous. You do see this quite a bit, like, but only in the context of like certain disciplines and stuff. For example, physiological saline solution used to prepare intravenous fluids has a concentration of 0.9% mass over volume. Okay, and that could be expressed as this M over V, indicating that the composition is 0.9 grams of solute per 100 milliliters of solution. All right. So what they're trying to say is that grams are equivalent to milliliters here, and that would be a unitless quantity, but in actuality it's not. It only works out when the solution has a density of exactly 1, and it's not actually going to be that way. So here's just an example of like the saline solution, and a lot of the diabetic test strips and stuff also will report glucose concentrations in mass per volume. ppm and ppb are parts per million and parts per billion. They're fairly common units that you may see, but I think they're often very misunderstood. Where they're useful is if you have really, really small concentrations. Okay. And basically what we're going to do is you start off by calculating it just like we did mass percent. Okay. Only the difference is instead of multiplying it by 100% for the parts per million, you're going to multiply it by 10 to the 6. So you're going to multiply it by a million. Right. So you can see that if the mass of the solute was really small and compared to the mass of the solution, this would be a really, really small number. And by multiplying it by a million, we can bring it up to a more reasonable value just to write down, just for convenience sake. And then part per billion is going to be the same sort of idea. We take the mass of solute, we divide it by the mass of the solution, we multiply it instead by a billion, 10 to the 9. And then you get the part per million and part per billion. And you see this quite often with really, really small amounts. Maybe you're talking about like water quality is a very common one. You're going to see that the safe levels of various heavy metals and stuff are going to be in the part per million or part per billion level. A convenient approximation whenever you're working with parts per million or part per billion can be done when the solution's density is close to 1 again. We can basically approximate ppm as milligrams per liter, and we can approximate parts per billion as micrograms per liter. And this is going to be true for most aqueous solutions. So most of the time when we have water as a solvent, we can approximate reasonably parts per million by these 2 units. And then that gives you just a little bit better foothold to see how you're going to use that in the problem and match your units up and see some cancellation.